about the extended Euclidean algorithm. For A inverse modulo n to exist, you would like the greatest GCD between A and n has to be equal to 1. If greater than 1, why can't we have an inverse? Okay. So one of the reason why I gave these kind of slides is to see basically the theorem proving version of the extended GCD algorithm. When the GCD is calculated between A and n, you will get two other integers. So this will imply G equal to A times x plus n times y, and you get in integers. This is true in natural numbers, integers, sorry, z, integer z, okay. Now then we actually gave from this one, I told you how you can find A inverse modulo n, correct. So and for that to happen, for example, when you take modulo n on such equation, this will become 0, and so you get 1 equal to A n, and that is the relations that you need for inverse of A modulo n. Okay, so you get the x becomes the inverse of A modulo n. Okay, so in general, the definition of inverse is given a number less than n, find another number y such that A times y equal to 1 modulo n. So conversely, you can say, let us say if A has an inverse, then you will find another number A, maybe some other, let us say A dash, such that it is 1 mod n. Now from the definition of mod n, when you do that, this particular congruence relationship is true for A dash equal to 1 plus any times n times y. Yeah. So if you find for example, if there is an inverse exist, then this will tell you that the greatest common divisor between A and n had to be 1. So if something goes on 1, that can never happen. So that is why for an inverse to exist, yes, A inverse should be so the greatest GCD has to be 1, which is the identity. Is that clear? Yeah. So that's the kind, it's a very good point to think actually. So many people find it difficult. So maybe I'll just run through this idea very quickly. So our idea was to given two numbers A and B, A greater than B, and here this is for example, you can for the purpose of mod n, you can substitute B to n, and this will go on. Okay. So idea is that when you are trying to find GCD of A, so first you start with this is an algorithm, extended Euclidean algorithm. So one version which can easily be expressed as a recursion. So you start with A0 is one of the elements, and A0 is greater than A1. You can take A0 greater than A1, A0 greater than A1. If not, just reverse it and you can continue, so not a problem for the algorithm. And then Q1 is a quotient. So you divide A0 by A1, okay, and choose the quotient. Now once you find a quotient, so you have that remainder equation A0 is Q1 times A1 plus A2. Now from our previous theorem, you can say that GCD of A0 and A1 is same as GCD of the smaller one of them, which is A1, and A0 modulo A1, which is exactly this. So A1 and A2, okay. So this is A2 is A0 mod A1. So that is the remainder. So now what you have to, you have now transformed the problem which was of a certain size to a problem where the size of the problem has decreased a little bit. Okay. So obviously then you can run again, you can take Q1 to be A0 times A1 and you can repeat it and so forth, and once at some point, because it is every time the argument is decreasing, eventually it will become 0 at some point of time. At t equation at minus 1 times the remainder becomes 0. So the remainder just before the one before, the step, that becomes the GCD. Okay. So, now once you get a GCD of AT 0, you can start working towards this one. So, by using the, so now using the fact that GCD before, GCD of AB is same as GCD of A1, which is A1, A2 and so on up to GCD of AT. And since one of them is 0, so the AT will be the GCD. So, solving for AT now look for the AT, and AT can be returned by expressing, so starting from the last but 1 to the first, we can express AT as a linear combination of A0 and A1, and you get back that equation. So, this equation is true in integers, and for example, A modulo B to, if you want to find the inverse A modulo B in that modular arithmetic, I should necessarily have AT equal to GCD 1. If GCD is greater than 1, inverse does not exist. Assume that, let us say, inverse exists, then I can set up an equation like this, A0, A1, and it is a modular equation. You can find some value to n which is true in integers, and then work backwards and show contradiction that GCD has to become 1. Because if you start with some numbers which is greater than 1, GCD greater than 1, and assume that there is an inverse, then you can work backwards and show that the contradiction, because GCD has to become 1. So, that is why this is a kind of strong thing to find an inverse of a number. Okay. Why I am doing it is because this is the basis of all finite field multiplication. If you do not get this one thoroughly, it is very hard to, you might do some exercises, and there you might say, oh, that is a 1, and some multiplicative structure, you can get some idea, but in order to understand the real finite field, this is the key equation, and this, this algorithm is been there since thousands of years. Yeah. In fact, the greatest common divisor GCD algorithm, extended algorithm, the version of one of the extended algorithm, say, let us say the modulo n is constant. So, every time in some application, you need to find out the extended GCD algorithm where one of the arguments is same. Okay. Now, how do you improve computations on it? And that is where you use Aryabhata's ideas, and so there is an Aryabhata's algorithm to reduce the steps in this and to make it very quick. So, you can go and you can search online and find out that one. This is given by Professor K something, somebody you can. That was an algorithm that also good, because as you can see that this is such an ancient idea. Okay, that is very important. So, now let us take an example of 33 from 31. I have worked through the thing. I think I gave a similar example there last time. Now let us say how that the penultimate step you can work back. So, you start with 21, 33 and 21, you divide, you get this equation, then 21 and 12 you get this equation, and so forth. At some point becomes 0. So, the 3 is the GCD. Now, you start with the penultimate equation, which is 3 is 12 minus 1 minus 9. Now, look, from this equation, from B you can take 9 equals to 21 minus 1 times 12, okay, and this is 12 minus 1 as it is. It is 12 minus 1 times this. Now, you rearrange. So, you can collect all the terms that are of similar. For example, here you take whatever that goes with 12 you put together, whatever that goes with 21 you put together here. But the next penultimate ultimate gives you from A, which actually tells for 12, and you instead of 12 you make it with 33 and 21. So, when you spread it or spread this equation, take this, you will have an equation only in 33 and 21. Okay. So, obviously now this is basically, see, 33 times 2 is 66 minus 21 times 3 is 63, and you get the GCD. So, and this equation is true in integers. So, if I want to actually get some relationship with modulo, one of them I can easily solve. So, I can get solutions modulo either 21 or 33 using this approach. So, here for example, when I say if I want to find out G is a greatest common divisor between A and N, I can find out the inverse of A modulo N or N modulo A, both is possible. Okay, you may be worrying, okay, what if one of them is small, how can I make a inverse of a number which is bigger than that? But does not matter, because when we find the inverse of number, we are not finding inverse of the number in integers, but the inverse of an which is, I will say, remainder. All of them is only remainder. So if one of them is bigger, you take modulo, one time you take out that whatever that is the inverse of that. So sometimes people you can get, when you are doing some small exercise, you might get confused, but then if you look at the remainder clearly, okay. So the remainders is the one which we are going to do, and all the remainder, whatever binary codes we talked about from last time, it is from remainders modulo 2, and because it is very intuitive and very easy, and also it has another explanation in terms of exclusive OR function. You may follow a combinatorics in one type, but if you want to do it in an algebra finite field, then this is the way to go, and this is what the thing. Okay, so I have already explained to this one, and this is the yeah. So again, someone was asking actually about the fields, rings, and etc. But now once you have, I also introduced actually relatively prime numbers. So this is what actually gives you help for the inverse of thing. So two numbers are relatively prime if the greatest common divisor is 1, and so one of the all these kind of number theory properties were actually studied by Euler in 17th century. He had done a great lot of research on it. So if you really want to look at about the basics of mathematics and all, is the contribution to Euler is very high. So many times Gauss also comes into a picture, and I will see some of these ideas how it comes, but Euler's contribution to it is tremendous, and one of them is called Euler phi function. It is also called as Euler Totten function. Okay, so given any number n, yeah, so this also will give you probably an intuitive and a clear understanding of what is ring and all. I will come back in it. So for n greater than 1, let phi on denote. So now given one n, now we will look at all the numbers be less than that, but are relatively prime to that. Okay, so you probably will be guessing actually what I am going to do. So when I choose n to be a prime number, all the numbers below n other than 0, they will have a relatively prime number. So they all have an inverse. That means that all the non-zero elements, if I can work towards it, that acts like a group, and so they can be divided, they can be multiplied. So you have an idea of a group, a field that comes from that when n is a prime number. But in order to think much more broader, the best thing is to actually idea of Euler Totten function. So given any number n, all the numbers less than that, but which are relatively prime to that number, what is that? How do that? So for that, this also sometimes you call that reduced set of residues modulo n. So when n comes now, let us take an example one itself. Let us take n equal to 7. What are the set of residues? Reduced set of residues. So set of residues is just between 0 to n minus 1, because any modulo n, set of residues is only 0, 1 up to n minus 1. Reduced set of residues is basically those numbers that are relatively prime to the n. So when n is 7, what is the size of the set of residues? 6, which is 1 less than that, because 0 is the one which does not have which is not relatively prime to that. So the reduced set is full, 1 to n minus 1, no gap in it. Whereas you take about 6, for example, when you take 6, what happens? So 3 divides, so and also 2 divides, 2, 4, yeah, only 2 will be there. So then you can actually try to now get an idea of understanding that. Now so the arithmetic over modulo n will depend on this idea, that is the reduced set of residues. Now if you know, with whatever that I have taught you, like whatever taught we discussed in the first 2 days, you should be able to compute this precisely without any doubt. And I give you a very simple thing. So there is already some examples are given there. Phi x is 2, and GCD of this one, and some I have given some algorithms for that, okay, some examples for that. But in particular, when I have a p is a prime number, this is p minus 1. This is already easy because everybody say everybody with it, that's easy, yeah, because it also comes from the definition. But let us take some number which is the power of p, like go to p square, that means number like 9, number like 4, number like 16. So now that is n, and now I want to find out how many are relatively prime to this. Okay, so can you prove this? And of course I have given it here. If you slowly see, you will see. Okay, so when it is 9, you know that because it's a only single power of prime, p divides that. So when p divides it, any multiple of p also divides it. So but you can easily count how many are there. From p to go to p square or p power a, you can keep on counting how many are there. And that is exactly the thing that I do. So there are exactly p power a minus 1 such numbers, including number 0. So all other numbers are relatively prime to p power a. Hence number of so if you want to find out this is basically, so there should be, there is a mistake there, do you see? So p power a is the total number of numbers up to p power a, and I am now excluding all the numbers that have something common with p power a. Okay, so that means I should subtract this number here, p power a, you will put a minus there in your thing, right? Then you take p power a minus 1 out, then so p power a minus 1. So as needed. Now think about why this is correct result. One way to do. Now when a equal to 1, that is exactly this result, and so you get that result. So that is why this result is a generalization of that. Now another way to prove perhaps is that now you assume that the like an mathematics, like a induction. First you make some simple calculations and you check that this is true for some p power small a, okay, some a, so p power, so p power 1, p power 2, p power 3, you can calculate by hand and it is true, okay. And then knowing that it is true for p power a, then you compute what is there for p power a plus 1, okay. So if you can express from that showing a step for I and step for I plus 1, then you would have shown it for everything, then it is true for all over a. So this is the kind of, so in mathematical induction, first of all you should show that the result is true for small set. So some function that is defined over integers, you can actually apply this mathematics. I made it very quick here, but perhaps some of you know already. So is it clear? Mathematical induction, you'll see some examples coming there. But did you see that I never use any other difficult mathematics, just to, you should be able to feel this, okay. Now the problem comes is that when the number now not exactly power of, so this is a ring. So you say because now p power a, now some numbers now can divide that, right. So that means that p power a, p to the power of a is the order of the group, and p power a is 0, because when you are looking for mod p power a is 0 in the residues, right, but p divides it. So but you can think that as because it is only one dimension, one prime number there, all the things. So there is also some other algebra comes into this is also called as a local ring, because it has a maximal ideal which is a field which is sitting at the end. So this is a small, the maximal ideal. So I had to go through other mathematics, but my resolve was not to use any other higher mathematics to try. But still you can see the ring, how the thing is there. Ring is because some elements can actually jump into 0. Okay, field everybody is except 0, they will be looking, all other elements just go around the field. That is what the Goulam wrote about, in Galois fields full of flowers, primitive elements dance for hours. So they in field is always except 0, all other goes merrily multiplying each other. Whereas in ring some elements can be, they can be suicidal, they can go to 0 and die. Yeah. So that's the simplest thing that you think about ring. Now this is a simple ring, you can also think simple, that is also called a local ring. You can make it assumption, but there are other, then you have to define about an ideal and so forth. It's very simple, right? But when it is multiplied by 2 primes, p times q, what happens? So can you do that easily? When number is just a product of 2 different primes, how many elements are there less than that which are relative to prime to that. So you can see that that also can be, you can also apply a same kind of thing. In doing so, you will come across another interesting combinatorially counting method that is mathematicians normally used, which is called as a inclusion exclusion principle. So when you are doing some computations in a systematic form, sometimes it is easy, you know, when I add something, I would have probably included something from the complementary set and then you exclude again. So this inclusion exclusion principle, you can actually show that phi of p times is p minus 1 times q minus 1, yeah. Did you see already why it is true? So if somebody can probably take it as they can tell me whether you can prove this one separately. And also then you can apply the same principles also. And there are other techniques also in number theory. It's called multiplicative functions. Some functions that you can find, you know, some functions are multiplicative in the sense if you apply for one value, then you get f of a and f of b. Then f of a times b is same as f a times f b. So there are functions multiplicative and this function happen to be that, and if you are a function you can prove it differently. So same idea what you can do, you can prove it in about 5 different, 6 different or 10 different, or you know, you can go on, even simple things, eh? So that is what you have to see, and so that is actually now semi-simple ring, because now the two numbers p q goes there, okay. So these are all the general things, but they have a precise definition in algebra. Then for that you need to go a little bit more, you know, for example at least vector space, which we will do later. So I think probably I have this as this is what actually what I meant by inclusion things which is already there. So for example, when I first exclude all powers of p, then I would have added one more thing, so then you have to actually at the end you have to do some more things. So this is what it is there. So please read through it and see whether you can follow this particular proof, okay. So also another one I said that it's relatively prime numbers. Then so only for those two relatively prime numbers, this is actually multiplicative. So but you know, there are some functions which is true for any integers, they are called strongly multiplicative ones. So if you do number theory course, there are lots of other things, but in general it's not obviously whether we have studied so far, but take this as a fact, you can prove this using some elementary number theory results. So so there is a I sometimes follow this book by Garrett. It's a very interesting one. He doesn't assume anything about mathematics. This is for anybody who is trying to do computing or engineering course in the beginning can do. So there are some type of thing. Also any number has a unique factorization, so you can say any modulo n, it has a factorization of this form and so forth. So this was also mentioned there, and some probability basics I think probably will use not there. Here this is a theorem that shows you that the extended Euclidean algorithm, I tell you, indeed give you greatest GCD, and I prove this results through this one. So this basically this idea of Euclidean algorithm is very useful. You know, any greatest common divisor, use the extended GCD algorithm. Please try with small examples on magma. The magma, I think we can send out the link, or you can just check magma online. You get a calculator, so you can enter the things that I did, you know, run through extended GCD algorithm, and you can do. I can probably show you simple things here. So it's a symbolic software. You know, you can define objects like in mathematics. I can define over a finite field, and I can work with a finite field, and you know, so that way it will be easy. And there is also so in this is, you know, for example x, g, c, d. If I type in, sorry, there are so many of them. Okay, so maybe I'll take the first one. No. So you can say, you know, ring field, you know, say for example extended greatest common divisor xgcd, it takes two number m and n, and GCD returns an integer g, x and y such that g is the greatest common divisor of the integers m and n, and g can be written as x times m plus y times n. So you can see x GCD times 23 times 71, you get a greatest common divisor as 1, and x times 23 times 34 plus 71 times minus 11, that is exactly equal to 1. So I can, using this I can do, if I say what is the 23 inverse? 34, yeah. So like that. What is 71 inverse modulo 23? 21, very good. Sorry, not 21, correct? No, 23 minus 11, 12. So you can see that the x is the 23 inverse modulo 71, y is the minus, this is actually 71 inverse modulo 23, okay, that tells you that. Okay, that is the proof given it here, and it will give you the answer. So I mean we are supposed to continue with the RAID, but what we thought is that RAID also requires some finite field things, and we are now probably at the right time to go through the polynomial rings and finite fields. So now so far we have seen finite fields as a modulo p or a modulo 2 or a simple objects. Now how to construct some more complex finite fields which are of interest in coding theory, and especially the topic under consideration. So at least now I will see what is a kind of a group. So now this is how an abstract representation of a group is done. A group is a set with a binary operation. So you have a group and you have a binary operation, and it follows certain properties, okay. And the first one is associative. So you can compute, for example, for any a, b, c 3 elements in the group. First of all, you should have a closure. Take one group element, another group element, and you apply the function, it should be in the same group. So that's kind of thing. But in associative is that for any 3 group elements, you first operate with b, c, and then operate with a, is same as first operate with a, b, and then c. So you get the same answer. Now within a group there exists an identity element E such that you can say A times E is 0, E times A is A. So this is there is always an identity element, and so here I am not specifying whether it is a multiplication or addition. The group requires just a set and an operation. In fact, most of the time the groups were initially discovered by symmetry. So it is not necessarily in a modular arithmetic, but we can draw some examples from the stuff that we have done. So for A belongs to G, now there exists an inverse element which is defined by A inverse, that is A times A inverse, you get an E, which is the identity. If the group also satisfies, for example, for all group elements A times B and is same as B times A, then it is called as abelian group, and this again named after another great mathematician called Abel, and he also died very young, like Galois, Abel and Ramanujan, both of them had a very short lifespan, but all of them made a tremendous influence on the knowledge in mathematics. So it is called the abelian group, yeah. Now let us come back to the things. A ring is now set R, the same set R, together with 2 binary operations plus and multiplication, such that with R is an abelian group with respect to addition. So take addition, the set is abelian and is associative, that is all these things. So for example, the ring you multiply in this way, associative property, but it also follows a distributive laws, that is for A, B, C belong to ring, the A times B plus C is same as first you can add and then you multiply, or let us say, actually I do not have to say, so it is customary to say sometimes this is addition and multiplication, but you can say plus and minus, you can call it by any operator, operator 1, operator 2, does not matter, but for convenience we will be mostly telling plus means addition, minus means the dot means multiplication, okay. And so as long as you are aware of the underlying group operation, that will be good, yeah. So this is the distributive thing holds this ones, okay, ring. So prime fields we have now, everybody understand, we can assume that it's a prime fields is fine. So it's a z, the set is up to p minus 1 and p is a prime number. So set is closed under addition, and p, since p is a prime number, any non-zero element of p also has an inverse. So because it's a prime number now, any non-zero element I can always find an inverse. So use the extended Euclid algorithm, find an inverse. So they are closed under multiplication, and they are closed under addition anyway, because that is how they are defined. So you can verify that the addition and multiplications are distributive, okay. So the thing, so like in Zp, unlike integers, p times any element in the field is 0. So this leads to called a characteristics. This is why I bent upon doing is, this is where the characteristics, most of the time when we do some problems in coding theory in a general class, 1 plus 1, if somebody recognize it as 0, means that they have understood one level, okay. So many people will be still in the level of 1 plus 1 equal to 2, yeah. So this is very important in that sense, the characteristics of that field. So why 1 plus 1 is 0 means it is the characteristic of the field is 2 there, okay. So all finite fields have a non-zero characteristics. So you can, so now I am giving you the meaning of characteristics in one other way. So but real numbers, the characteristics, what is the characteristics of a real number? See, what is then any non-zero element you have to keep adding. So in this case, in a modulo p, the characteristics, I have a definition coming up there, but just to kind of thinking about these objects, it helps. For example, take any real number, after taking some non-zero real number, how many times you can add, you can never get 0. So they keep on adding one of them, it will only grow, it can never become 0, right. Whereas with modulo p, you start with 1, you go 2, keep on adding 3, after p divide is become 0, so it becomes 0. So it can become in a magic, it's going to, something that is growing up, it becomes completely 0, but in real number it can never happen. So it's customary to say that the real number has a characteristic 0, that means you can't make a non-zero out of 0. So that is why, but all these fields are actually non-zero characteristics. So now let us see, let f be a field with a multiplicative identity 1. So we can, so sometimes you can have a, you can define when you have a field, what is a multiplicative identity, what is the additive identity. So additive identity is usually 0 in our application, multiplicative identity is 1. And the additive identity and the characteristics f sometimes is written as char of f is the smallest integer n greater than or equal to 0, such that addition of the 1 with itself n times results in 0. So that is when I am taking 1, which is a multiplicative identity, and keep on adding what is the smallest integer n such that you add 1 that many times gives you 0. That is what is the definition of a characteristic. Is that clear? This is a very important to recognize these characteristics. So note that for real and complex number you cannot find a positive integer n satisfying the above criteria, hence the characteristic of real is 0. So in contrast, residue class integer n, the characteristics is n, okay. So when n is a prime number, it is a field according to the characteristic is p. So Zp is actually main source of prime fields. However, from algebra we know that the finite fields of size of prime powers exist. So then you go, I do not want to do a lot of algebra now. I think if you go there and say that people think about, okay, here is these objects such as finite fields, how many are there, how are there, and there is a theorem saying that all finite fields are of the form either prime or prime powers. So far we saw a finite field of prime, so that which is generally obtained from prime numbers that are given from there, right. So how do you construct a now finite field which is of a prime number, and that is what the idea. So that is where we come up with another type of rings called polynomial ring. So this kind of rings are a bit different than the ring that we talked about, but they in a sense that they also have for example a integer ring is also called as a ring. integer ring, because you can add, multiply, and it has it's also sometimes known as the integral domain, but it's in the algebra there are a lot of things, but we will not go into the precise definition. But now I am now giving you another ring which is called polynomial ring, which becomes very important for us to use, and in fact for the next 2 days in Reed-Solomon codes and other things we do need these ideas as much as possible. So how I define now a polynomial over a field is now expression, so which is f0, you use an indeterminate and you make it like a field. Okay, so you have a f0 is a scalar that is in the field, and then you can this is what it means, where the symbol x is indeterminate and the coefficients fi are elements of the field. So you take the elements of a field, another given field which modulo p, they throw in x and demand that it has all the properties of ring. Okay, this x is, think of this way, this is how to think of mathematically is this way. So f is already we have understood now, it is a finite field, and you can name them, it is 0, 1 up to p minus 1, there is nothing more than that. We can and you can do add, multiply, all of things we understand, and we demand similar properties, then we take another integer x and we just throw it to this set and demand you also behave it like whatever I said, okay, like add or something. Now what happens moment you do, some great thing happen. If you put x there, x times x also should be there, so x square should be there. So if you take up an integral polynomial, I mean here I give a polynomial definition, but in general moment you have a field and I put x is there, x square is there, x square times any number between 0 to p minus 1 is there, then x cube will be there, then x cube plus x square will be there, x4 will be there, then it will so on go up to infinity, x to the power of infinity. So now you artificially create another polynomial ring which is almost similar type of integers. Okay, and that is what happens. So you have so now we need some definitions. So you need to, when you are treating with this, like 0 to p minus 1, that is okay, you can use the numbers. So here a 0 polynomial is 0, fx is equal to 0, which is this 0 will be same as what is there in the underlying field. Then the degree of a polynomial now, so for example one polynomial is bigger than the other, how do you do? Depends on the degree. So the degree of the polynomial of x is the largest index of the non-zero coefficient. So for example degree of 1 plus x plus 2x cube is 3, okay, and you can also, the degree of 1 times x0 is to be 0. In general the degree of a non-zero polynomial is always finite. By convention if you have a 0 polynomial then it is infinity, minus infinity, that is by convention. Okay. So polynomial of degree n is monic provided the leading coefficient of the index is equal to 1. So whenever x power n, so for example this is not monic but this is monic, because here the coefficient of the highest power is 2, here it is 1. So you have a monic idea, and two polynomials f of x and g of x are equal if the coefficients fi g are equal. So now I also need the equality. How I had to compare two polynomials. When can I say two polynomials are equal? When they are equal in every coefficient. So set of the polynomials over a field is denoted by f of x. So now you take, this is what I said mentioned. So for example how these polynomials will come basically is just taking a field f and throwing an index indeterminate x, then you get f of x, which is like a big reaction, and suddenly we have a finite set. You have a finite set f, by putting indeterminate x you become an infinite set, and that is what we do. So analogous to integer addition and multiplication, we can also define polynomial addition and polynomial multiplication. So just like that. So this is the things we do. So first one is sum is very easy to see, yeah. So f of x plus g of x, you take every coefficient, you take modulo p here, whatever the addition is in the field, whatever the field is there you can add, and then you can collect all the corresponding terms and you do. So you can, there are some examples are there, and the product is basically you do the same thing except that now you just multiply like with polynomials. For example, if there are x in here, it becomes x squared and so forth, just like a polynomial multiplication. And you can actually have an expression for that, and sometimes those of you coming from electronics, the signal processing thing, you will recognize this multiplication as a convolution, discrete convolutions. In fact, what you do in signal processing is basically a polynomial algebra. Yeah? So just a polynomial, all the Laplace transforms, everything what you do is polynomial things. Yeah, and x becomes a delay there. So when you are trading with signal processing, x becomes a delay, and you can work in the same way. Okay. So some facts that you know, because we don't have so whatever that we did with the integers, with you know, because it's an interesting one, you could do the same thing. So we don't have much time, so we will go through that. So if fx is if any fx in any fx for a polynomial ring, subtraction is always possible, but division is not always possible. Okay. So because subtraction you can always do, you can subtract one over the other, and in the morning I explained to you, subtraction is basically taking the additive inverse as a scalar and multiplying the second polynomial with additive inverse and adding it. So its minus here is p minus. So only in binary field the additive inverse is 1 itself, 1 and 1 are additive inverse, so you don't need to think minus and plus are similar. But in other cases, if you are subtracting it in modulo p, you have to multiply by p minus 1 to the second element and add pointwise, because all the corresponding indeterminants need to be added. That is what the addition and subtraction there. But division is not always possible if I try to do. So if you take a polynomial Rx, so for, let us say if a polynomial Rx divides another polynomial Sx, we say that Rx divides Sx, and Rx is divisible by Rx and is a factor of Rx. So just like we have factors in integers, you can now polynomials dividing one another. For example, 1 plus x divides 1 plus x divides 1 plus x to the power of 2 and that could be anything, but that divides. Okay. A non-zero polynomial px is divisible by px or by alpha, where alpha is arbitrary field element, is called an irreducible polynomial. Okay. So now when you have a non-zero polynomial that is divisible by px by by itself or by any scalar element, then so an idea of divisibility comes. So once I have a divisibility, then it's just like the idea of a prime numbers, you will get a prime polynomials. Okay. So monic irreducible polynomial is called prime polynomial, and once with the same idea I can think of a greatest common divisor between these two polynomials, and that greatest common divisor of two polynomials is the monic polynomial of the greatest degree that divides both of them. Okay. So through some examples is there, that should be help. Okay. So then you have a greatest common divisor, then polynomials are relatively prime, then you can also have a division for LMS, the LCM, which is the least common multiple of these two, and you can have a division and Euclidean algorithms defined over integers analogously extend to the polynomial rings. In fact, when you have written an algorithm on Magma for integer, say Euclidean algorithm given here, you could just change the domain from integers to polynomials, that will work for here as well. So it's the same algorithm works for the polynomials. Clear? Yeah. So after coming there, I need to actually show you how division happens here. So an example would be first going to go through. So 2x to the power of 5 plus x to the power of 4 plus 3 is now f5. So okay, now f5 is z5, which is the integers modulo 5. 5 is a prime number, 0, 1, 2, 3, 4. Okay. Now 4 is actually minus 1 in that field. Do you see? So maybe just to kind of to make it very simple, I'll put now 0, 1, 2, 3, 4. Now 4 is actually minus 1, 3 is minus 2, this is actually minus 3, this is minus 4 and 0. You can represent it like a 0, 1, 2, 3, 4. So this is minus 1, minus 2, minus 3, minus 4, minus 5. Sorry, this is 3. Okay. Yeah. Yeah. So it's you have a long division. So everybody knows about long division that you do polynomial. It's the same type of thing. Say for example, you have 2x cube plus x4. So I want to divide by 3x square. So really in the first step in the division is, first of all, whatever that quotient you do, that when multiplied by the quotient, sorry, this is the divisor, the degree of the highest degree of the divisor, and what you are trying to divide, first of all should match. So first you take x square, so you need x cube to cancel x5. So first you choose x5, x cube, and then what you do, normally you multiply, and then this is like same way you multiply in integer, divide in integers, in the same idea. So if you want to say 521, first you say 23, say 5 times, okay, 4 is nearest one is 20, then you subtract, and that's what you get, right. The same thing you do here, you choose here x square x cube, so there is a the x square goes with so x5 x square, so you need x cube there, but then when these 3x square when multiplied by whatever it is should get you 2 here. So basically what multiplied by 3 will get you 2, so 3 is actually minus 2, so you need a minus 1 there, so 3 minus 1 is 2x square. Okay, so 3 times 4 is 12, modulo 5 is 2 also you can say, so they become same, then you subtract. But you do this for everything in this. So once you have chosen a quotient, then you have to multiply all towards the whole divisor. So that means 4x cube as well come. So that's what you multiply, and then you change the sign because you are now subtracting. Now this goes cancels, so the remainder now has become of degree 4. So with this one step now, the remainder has become degree less than the previous one, but still the divisor is degrees more, so still you can continue. So you can continue until the remainders, the degree of the remainder becomes the less than that of this. That's time this division. This is just one division, right? Whereas in one step you get that idea. Here you may have to do through thoroughly. Okay. So this one in corresponding integers, this is equivalent to one step, and I do that's actually one step. All right. So you can do that. So same way you can try and do. Okay. So we will I think probably we'll do some of these proof before we go, at least time is over there. So how polynomial rings are different to integer rings, so I have some own ideas. Firstly, even though polynomial rings over ZP is an infinite size, what you need to recognize that it has a finite characteristic. So I have a polynomial which can be of a very big degree, so the size is infinite, but if you look at the characteristics, like take any polynomial, say 3x square plus 4 in this one, okay, say 3x to the power of plus 4, which is modulo f5 of x, right, f5 of x. Okay. But if you keep on adding p number of times, whatever may be the big size of the polynomial, you add p times, that becomes 0. So the characteristics of this polynomial ring is finite, and that's precisely equal to the characteristics of the underlying field. Clear? This is a very important concept. Characteristics of this big integer ring, which is an infinite ring, it is also finite, because you created out of g of p, which is finite. This is that's what I call this as a man-made, yeah? Whereas integers is God-made. Yeah? It's big, nobody has made it, it is already there, and there it's a different ball game. Whereas with the man-made, we can start with finite, whatever we understood, and we can make it infinitely, but the characteristics is still p. Okay. So do you see this idea, this one? So now in fact the polynomial rings, the character is same as the underlying field. So prove the following result. this is, but a plus b to the power of p is a to the power of p plus b to the power of p. So those of you have done, say, in your high school years, you've been given some, what is that, a plus b square is how much? A square plus 2ab plus b square. Okay, what is a plus b whole cube? A cube plus a cube plus b cube, 3ab plus yeah. So many formulas you do like that. So this is a kind of an idea of expand. Yeah. So it says a plus b. Sorry, I shouldn't write it up top, right? A plus b to the power of n expand. Okay. So in a mathematics class, this was given, a plus b expand, and in fact student didn't know, so he started expanding like this. Big size. Yeah. So so once it becomes n, how do you expand it? So some of these things you would know. For example, how do you prove that a plus b to the power of p is this? You have any clue? So pardon? Yeah, go ahead.
A raised to n plus nci.
Yeah.
Are multiples of p, so they all become zeros.
Yeah, that's. I think some of you already know the proof, but I think I've just given some things for here. So this is basically probably not written in a nice way on the slide, but I think if you read and if you get that idea, that's good enough. So first we prove the, first this is called a binomial theorem. So probably I'll leave it for you to think about this one, because each one and see in how, for example, proofs can become subtle and it become very clear. You need to have that knowledge at the end of that should be clearly obtained from the initial steps that we start with. That's the idea of a proof. So in this case a power p. So the idea of this here is, when you raise it to p, I don't the advantage is I only do this here. So for example, I said a plus b to whole square is a square plus b square plus 2ab, but for any characteristics field 2, the 2 goes away, so things becomes pretty easy, simple. Yeah. So that's what we do in here, the polynomial rings thing. So I'll leave these two to think about it, and if we require we can talk in other time. And same way I can also finally the proof is actually everything is given here. So how polynomial rings are different to integers, this is what I said, is that the another difference is the nature of the factorization problem over the ring. So you take the problem of factoring polynomials over ZP is not at all hard. In fact, if you given a polynomial over a finite field GFP, you have actually very efficient algorithms to factor them. So this is given by Berlekamp. The coding theorist, if you actually look at the algorithm is there, it's pretty easy. In fact, but on the other hand, factorization problem over integers is still hard, and nobody knows whether it's hard or not. In fact, we don't know the complexity of that algorithm. There are lots of people are thinking about it, and a lot of big research groups are working to factor it. We have got many algorithms, and probably now people can factor numbers of the size as 300, 400 bits pretty easily now using cloud computers, help of and others. There are possibilities, but still people don't know whether there's, for example, you have an algorithm that works for up to 500 bit. If I increase the size to 501 bit, the same computer, it can take probably years. And so we don't know the complexity of the integer factorization, but for the polynomial factorization is pretty easy. In the early days of cryptography, people thought that they have a new polynomial algorithm based on polynomial factorization to see that within few on a month another person coming up with the hack, because because polynomial factorization is not a hard problem at all, and so you can't base any crypto on this. So I think probably we'll finish off the construction of this one, so we can start the next one. So formally the set of all residues of polynomials can be obtained with a prime polynomial. So you take a g of p power k is basically choose the polynomial ring and modulo mx and the irreducible polynomial of degree k. So we will work through some examples. So what I have done in this case is basically going through whatever I speak in a simple, because this was created for students who had difficulty in actually understanding the finite field. So I have whatever that goes in explanation, I have just written it in the same form as required for them, and it was taken out from some explanations that I give from their discussion forum questions and exactly how to do it, and also some kind of ideas working behind that I have mentioned. Okay, so but maybe the simplest thing one be to really to think of, because it's a polynomials, they are vectors. Okay. So now for example here I am looking for g of 2 power 3, which is g of 2 everybody knows now by now, and I want to create a finite field of size 8, then I look for irreducible polynomial of degree 3. Okay. Now irreducible polynomial of degree 3 you may have some problem, but that I will help you to solve easily through this idea. So for example, when you consider polynomials, now x is it irreducible over g of 2? But that means I cannot find x is irreducible because you can't find further factorize this number into two numbers, right? So and the same way 1 plus x is another polynomial. You can't factor this further. So 1 plus x is actually into 1 plus x. I can't divide that. But let us now go to degree 2. So this is the degree 1. So this is the polynomials in g of 2. So let us go to degree 1. So let us say degree 2, if I go, how many polynomials are there of degree 2? Now polynomials start with a constant term. So there are two possibilities for there, and degree 2 x will have two possibilities, and degree 2, so how many? 2 raised to power 3, right? 8 polynomials are there of degree 2. So out of that, for example, x square, is it irreducible? No, because x square can be written as x times x. So it is not irreducible, it is reducible. So x square is out. Okay. Can I take 1 plus x square as irreducible? Yeah. Now try. You can't, because I divide 1 plus x by 1 plus x square, it divides. So this cannot be. Okay. So you can see that 1 plus x squared is same as a plus b whole squared kind of thing. 2ab is anyway 0. This is 1 square x square. So and we had proved that a power what is that, a plus b whole square is same as a square plus b square in g of 2. Okay, we had proved in g of p is the same thing. So this can't be. So you can take 1 plus, if you'll find that 1 plus x square is the only irreducible polynomial of degree 2. So again, like in the numbers I told you, after finding these irreducible polynomials of certain degree, all multiples will be reducible anyway. So you can rule out. But probably for polynomials you don't need to do such, because that's not efficient. But the 3, if you go, you will find 1 plus x cube and 1 plus x square plus x cube are the two polynomials you will see, and I have used one of them in this one. So let's go back this. So once you do, let us say 1 plus x cube, what I do is that I take the elements now as a polynomials. So 0, 1, x, I can go, because these polynomials, so here these polynomials are residues now after dividing by 1 plus x cube. Okay. So up to 1 plus x square, if you divide by x cube, because it is degree less than that, the same thing will, you will not, the reminders are exactly what is that. Okay. But then after that you have x cube. Now if you try to divide x cube, what will happen? So now x cube and I am now dividing by x cube plus x plus 1. So, I want to cancel the leading coefficient and 1 is the quotient, x cube plus x plus 1. So, this goes and then the subtraction here, but in this case it is same, you get x plus 1. So, x plus 1 now whose degree is less than that is the remainder. So, that is what the x plus 1. Now, x to the power of 4 you could do the same thing, but since x you know x cube, you can find out x to the power of 4 is simply x times x cube. So, which is you just multiply here, x becomes x and x by x square. Since the degree is less than 3, you can still retain as it is. Then if you multiply in the same logic x square plus x cube, but x cube is already x plus 1, now you can replace by x plus 1 and you get this value. So, next one you go there, here this become a multiply by x becomes x times x square, then x cube is x plus 1, then you get 1 plus x square. Then multiply by x again, you get x plus x cube, but x cube is x plus 1, x cancels and you get back 1, and then you multiply by s, you get back. So, all these elements are now are of degree 7, and you know for example x multiplies with itself, actually you get all elements of the finite field, and all of them can be expressed as polynomials of degree less than or equal to 2 or less than the degree of the polynomial. So, the finite field polynomial finite fields now using an irreducible polynomial you can create as vectors, but now what you are talking is residues of polynomials divided by the prime polynomial. Now, of course, I had to choose a prime polynomial. There are some more mathematics you need to understand how to get a prime polynomial, how to get just irreducible polynomial. So much of work is there, but let us say to understand the concepts, like from today's topic was basically what is that what is that fieldness or ringness. He said this is the fieldness of that, it comes out of this value, this idea. So I want you to kind of learn from each other and somehow master how you do these equations. So that will actually help you to think further thing, because what you do when you define codes now, we will take care of the size of this field. So this size of this field becomes let us say is 8, and the non-zero elements is 1 less than 8. So I am going to now look for a length of the code to be something divisible by this number, because that I can now handle constructing them through this primitive these elements. Of course, I will name x as alpha in some case, beta in other case, two things, but we know exactly the meaning of these things. Okay, so if you know that, that will be that's a crucial thing, because if you don't get those doubts now, you will get it later. So better if you are not getting any doubts, means that you are not you are not understanding something. That's be clear, especially in these things. But when you start doing, for example, g of 2q, maybe you try to now express the same element finite field using another polynomial of degree 3 given by 1 plus x square plus x cube. The equations looks a bit different, and so probably redoing that by hand will actually help you think. So and in order to show you that this particular process is similar, not just only for GF2. In GF2 there are certain other improvements can be done. For example, here I can also express these polynomials as vectors. So you take 0 here, all 3 vectors. 0 is actually not just the 0, it is actually a vector of length all 0. 1 is 1 0 0. So when you multiply by x, so you can see that it becomes x is 0 1 0 and x square is this. So all other elements as actually expressed as a linear combination of these. So that means all other higher powers here, what you see, can be expressed as a linear sum, and you see, you already see a vector space over this. Okay, so vector space definition is only, so in fact the underlying the alphabet here with GF2 GF2 square, if I don't insist on the field properties, it's a vector space as well. So and it has all such properties. Okay, so but the field GF2 power 3 of size 8 is unique. So whether you use this polynomial or that polynomial, you get the same object, because the multiplicative group is of length 7 and so forth. Okay, so you see the point. So in fact, fortunately for this polynomial, there are only 2 polynomials of degree 7, and you can see that if I leave out this particular 0, I am just giving you another interesting observation. You can see, take out this 0, so you get all this number starts with 1 and it ends here like this. It's like a period, and now you look at this number 0 0 1 0 1 1 1. So 1, you can pick any one, but let us say check the first one itself. Okay, so you can see that in here I'll start counting this number, this sequence, which is written from top to bottom. I leave out the first one, leave out the last one, because it's a joining thing, right? So you can say 0 0 1 0 1 1 1. What is the length of this vector? 3 6 7, which is 1 less than the field, right? Now in this field you can see now 0 0 1 is one pattern, 0 1 0 is another pattern, 1 0 1 another pattern, 0 1 0 0 1 1 1 1 1. Now if you wrap it around, because it's a periodic one, 1 1 0 is another pattern and 1 0 0 is another pattern. So if you take it like a periodic sequence, all possible 3 tuple occur exactly once and everything is there. Now because there is a 2 zeros there, and you can actually make it of length 8 by stitching 1 0 artificially, then you have a length 8, all possible 3 tuple occur exactly once. So now this sequence has a very interesting property. So let us say you have a combination lock, you have sometimes a lock which when you open, yeah. So you need to have, let us say, all 3 correct word to get it to open the lock. Now if you need to do this, try out all possible 1, you may need to go through, first you try 0 0 1, next 0 1 0, so like that you will see, you will try 27 times 3 21 times. But if you use one such sequence, because it has all possible 3 and together, within 7 you will open the lock. Okay, if that lock has that property of it accepts the consecutive 3 steps to open. Yeah? So this is why this is one way of doing it. And in fact, if you look at this is very interesting one. If I use the other polynomial, the sequence I get is the reverse of this polynomial. In fact, the reverse of that sequence. For example, I started here, right, 0 0 0 1 this one, but if I choose the other polynomial, I get the reverse of that. So, and in fact there are only 2 such sequences in the universe having this property with the linearity property. Okay. So one of them actually is used to represent poetics. In Indian poetics, you have have you heard of Yagana Magana Tagana, like that? Just you want to have let us say you have a poetry, and the poetry intonations, something will stay for a longer, something will stay for some consonant will stay for a shorter one. So then the particular attribute you do it is the way you get. For example, one lagu guru they call it. So some word which is stay for a longer time, the shorter time. And I want to remember all possible 3 types, right? And so the best way to remember them is by having a length of sequence 8 with this one, and this comes from this polynomial. So they have used one of them to remember. So this is comes Yamata Rajabhana Salagam. So if you remember that, so the first letter of that will tell me what is 1 0 0 1 1 0. So you can do that. So I mean, for example, this is just a little bit digression, but you can see some other interesting aspects of finite fields in this. So this can be used to do for many operations, not necessarily for the coding thing that we considered. So G of 3 square is also I have explained in another way, same idea works through. So I went a little bit faster, but hopefully because it's all written down very clearly, so you can probably understand that. And some idea of a primitive irreducible polynomial, how to get it, that I have discussed here a little bit, but we probably don't need that much, because you can take it for granted that when we are constructing a certain polynomial, so you've been given with that polynomials with that property at this point of time. But once we go further, we can do okay. So this we will stop it here, and we'll come back and see how to efficiently. So probably please do some exercises like try this with another polynomial. You can do and come back and ready. So now that we have we have described all finite fields now. So we can work towards vector spaces over finite field, and we'll start working for higher codes defined over higher alphabet. So from binary to non-binary, and that helps us to come up with Reed-Solomon codes. Yeah? So please read through this slide, because the different meanings associated with handling these polynomials, like some people say 0, and shortcuts that you can use to quickly compute things, also explained in one way or the other. Okay.